Hello from Chem Help ASAP. In this video we'll do some problems in which we draw multiple resonance forms and then rank the resonance forms based on their stability. Go to the description of this video to find links to printable copies of these problems as well as printable solutions. This video also contains links to other videos that might help you with this material. Let's review some ideas before we do the problems. First, let's quickly review resonance. So there are three scenarios in which we encounter resonance. The first is normally we have a double bond next to an atom with a lone pair. And we can swing those electrons down to draw a new resonance form in which the lone pair becomes a bonding pair and the pi bond is broken and becomes a new lone pair on atom A. Now I haven't identified what A, B, and C are, but if they are neutral on the left, then A would be negative on the right and C would be positive because C has lost electrons in making that bond and A has gained electrons in getting that lone pair. The second scenario for resonance, which is not nearly as good, is when you take a pi bond and you simply break that pi bond and you put the electrons on one of the two atoms. So I've put the electrons on A. You could just as easily have put them on B. If A is neutral on the left, it'll become negative on the right, and B will become positive on the right. This is less satisfactory. Typically means that you form atoms that don't have a full octet, but we'll see this some. The third scenario is almost always limited to carbocations. So you can imagine having a carbocation with a vacant p orbital, and now when we move the electrons, we don't have a lone pair. We're going to actually start with a bonding pair and move that bonding pair like so. And we will simply shift the carbocation as we move the double bond. So this is a little less satisfactory because both structures don't have full octets, but those are in fact resonance forms. So now let's move to Lewis dot structures. Lewis dot structures, the number one rule for drawing a good Lewis dot structure is to have full octets for all your atoms. Now if you can't get full octets, then you at least want to minimize your formal charges. And of course, if you can't get rid of all your formal charges, you want to look at the placement of your charges. And when I say placement of charges, I mean if you can put the negative charge on something like oxygen, which is more electronegative, that is better than putting the negative charge on nitrogen, which is less electronegative. And the opposite would go for positive charges. M plus would be better than O plus because nitrogen is less electronegative. So those are the basics for resonance and Lewis dot structures. Okay, here is our first structure in the upper left. Our first job is to draw a Lewis structure. We don't have to draw the entire Lewis structure, but let's just make sure that we show all of our lone pairs. So here is our structure drawn with lone pairs. That would be resonance form number one. Now let's redraw this resonance form. And let's show an additional resonance form. So I'm going to break that pi bond and put those electrons up on the oxygen. That's going to give oxygen a negative charge, and a result, the carbon has a positive charge. So this is our next resonance form. It's our first one. Let's go back to our resonance form, our original one, and now let's break that pi bond the other way. Put the electrons on carbon instead. Well, now oxygen still just has two lone pairs. It's going to have a positive formal charge, and the carbon picks up a lone pair and gets a negative formal charge. So these are our three resonance forms. How do we rank them? Well, first would be this one. We have full octets and no formal charges. Now in the other two we have formal charges, and we look at where we place them. in the top structure we have a C plus versus and an O minus. So that's better than having an O plus because oxygen's more electronegative, and a C minus because carbon is less electronegative. So this would be number 2, and this would be number 3. So when we think of our contributors for the resonance forms for this molecule in the upper left, we would say its structure best reflects the number 1 structure. It's got maybe some minor contribution from number 2 and really minimal contribution from number 3. Here's our structure in the upper left. Let's redraw this with some lone pairs and bonds as our original resonance form. This is a Lewis dot representation of that structure. So here's our first representation. Now let's redraw it. And now we're going to mess up this picture to draw a new resonance form. Note that this structure has our most common feature for resonance, where we have an atom with a lone pair, atom C, and next to a double bond, A and B. So we can take our lone pair off of oxygen, push it down, make a new CO pi bond, and break an old CO pi bond. That gets us to here. Just one lone pair on that oxygen now, and it will have a positive formal charge. So there's a resonance form. We can also start with our original structure. And now we can simply break the pi bond. We can take these electrons and break that bonding pair, put it up onto oxygen. This oxygen in the lower right stays the same, and the carbon will have a positive charge. So these are our 3 resonance forms that we've drawn. Which one's best? Well, note the top 2 both have full octets. That has full octets and that has full octets, but the one on the right has formal charges. So this one is best. This would be number 2. And our bottom structure doesn't have full octets on carbon. That's has an open shell. So this would be number 3. So when we think about our structure in the upper left corner, it would the resonance form that most is the greatest contributor is number 1. There may be some properties of number 2, minimal contribution from structure number 3, resonance form number 3. Here's our new structure in the upper left corner. Let's draw this with lone pairs. Carbonyl oxygen has 2 lone pairs. Now we have a negative charge on this other oxygen. So we have 3 lone pairs. Great, so this is our original resonance form. Let's redraw that and move around some electrons. So we have an atom with a lone pair next to a double bond. We're going to use one of those lone pairs to make a new double bond, and we will break the old double bond. Now we have 3 lone pairs on that oxygen, just 2 on the other. There's our second resonance form. And to draw the other, we're going to have to do something different. We're just going to break this pi bond, and we're going to put that bonding pair of electrons as a lone pair, a third lone pair on oxygen. The other oxygen still has 3 lone pairs and a negative charge, and that carbon will be plus. So there are our three resonance forms. So this structure has full octets. It does have a formal charge. This structure has full octets and a formal charge. And you might say, those look like the same structure. They are the same structure, but there are definitely 2 oxygens in this molecule, and both of them can share that negative charge. So these are called degenerate resonance forms. Degenerate is not meant to be an insult. Degenerate just means they have the same energy. So this would be number 1, the structure on the right would also be number 1. They are equal in energy. They are equally good contributors to the overall picture of our structure in the upper left. Now, this structure in the bottom is not as good because we have a carbon that doesn't have a full octet. So this would be number 2, and it would be a distant number 2. So here's a case where we have multiple resonance forms, and some of them have the same energy, equal stability. We call these degenerate resonance forms. All right, our new structure is in the upper left. Let's redraw this and fill in our lone pairs and such. There's really not much to redraw for this structure. So here's our original form, and that's our first resonance form. So let's redraw this again, and let's show some resonance. Now, I tend to start with lone pairs when I think about resonance, but those lone pairs are not next to a double bond. They're next to a sp3 hybridized carbon. We can't just dump those electrons down to that carbon because that carbon already has four bonds, 4 sigma bonds. We're not going to break anything. So those lone pairs are stuck. So we can still talk about resonance, we just can't involve the lone pairs. We're stuck with discussing the double bond. So let's try moving the double bond to one side. That would give that carbon a lone pair, give it a positive charge. Now let's redraw our original structure and draw yet another resonance form. And really our only option is take the pi bond and push it down to the lower carbon instead. That would mean that the left carbon would have a positive charge and the right carbon has a negative charge. So here are our 3 resonance forms. So I think it's pretty clear this one's going to be the best. We have full octets and no formal charges. That gets the number 1, that is the major contributor. And as we look to the right, now we have both of these. There are a few ways to look at these, but I'll take a look at the charges. The charge in the top one, this is a tertiary carbocation, and this is a secondary carbocation. You normally think of tertiaries as being more stable. In terms of the carbanions, the top one is a secondary carbanion. And secondary carbanions are considered more stable than tertiary, at least in solution. And finally, I'll throw one other factor. This carbon-oxygen bond is polarized, and that would put a partial plus on that carbon. And so what we're showing is an inductive effect. Just say induction. That's an inductive effect. So that polarized bond would presumably stabilize the negative charge next to it, as we see in the top structure. So this one is looking better for multiple reasons, and that means the bottom right one is number 3. Not that I'm crazy about number 2 or 3 because they both have carbons that don't have full octets. But if I had to rank them, that's how I'd rank them. So for this structure, number 1 is this structure on the far left. That is by far number 1 major contributor. And then number 2 and 3 are both minor contributors, with 2 maybe being a little bit better than number 3. In the top left, we have benzene, such a simple structure. So there's really nothing to draw for the other resonance forms. So okay, here is our original structure. That is our first resonance form. Now, what are we going to do for resonance with benzene? Well, one thing that people often show with benzene is simply shifting the double bonds in the ring. That would get us to this structure. It's very subtly different from the first structure. Again, we're going to use this idea of degenerate resonance forms in this problem. But let's draw the third resonance form, and then we'll get into some of these comparisons. So for the last resonance form, let's redraw this structure, and let's simply break a pi bond. We can always do that if we have a pi bond to generate a new resonance form. So that would give that carbon a lone pair and a negative charge, and this carbon would have lost its bonding pair and would have a positive charge. So here is our third resonance form. When comparing these resonance forms, we would say here's this structure on the far left. It has full octets and no formal charges. Full octets and no formal charges on the right as well. These are two resonance forms, but they're different. They are different structures, but they have identical energies. These are degenerate resonance forms. And then the bottom structure is a second minor contributor, like very, very minor contributor, but we can still draw it as a valid resonance form. Note that it's because of these two degenerate resonance forms that sometimes people draw benzene as if it's a combination. If we isolate this bond here, between the two resonance forms, the two major contributors, we see that that bond has double bond character on the left and single bond character on the right. So people will try to approximate that by drawing a dotted line between those atoms. And if you look at all the other carbon-carbon bonds for benzene, you can draw all of them with partial bonds. So this is a way to try to show that both those resonance forms are contributing at once. Note that this bottom structure is not a valid Lewis dot structure. For Lewis structures, we have to commit to our major contributor. But that is an alternate representation, and some people take this a step further, and they just draw a circle in the ring. But we're going to stick with proper Lewis structures, and we'd say these are two degenerate resonance forms for benzene. Here in problem 6, we have an amide as our structure. I love amides and resonance. Amides were made to highlight resonance. So here is our original structure drawn with its lone pairs. There's our first resonance form. Now let's redraw that resonance form and let's see if we can come up with some other resonance forms. So this has the classic example. We've got a double bond next to an atom with a lone pair. So let's move those electrons. 1, 2, 3 lone pairs on nitrogen. We'll now have a carbon-nitrogen double bond. And that nitrogen has a positive charge. There's a resonance form. Redraw our original structure. And let's come up with another resonance form. And we're just going to break the pi bond. That is always the cheap out to make a new resonance form. Typically, these are terrible because you get non-full octet structures. But it does give us another resonance form. Okay, so now we have our third resonance form. Let's do a little compare and contrast. So for our first resonance form, we have no formal charges and everything has a full octet. Gold star for that particular resonance form. That's going to be our best one. Over here, we have full octets still, and that's great, super important, #1 rule for Lewis structures. But we are getting some formal charges. So this is not as good, and it's going to end up being #2. And our bottom structure, we have formal charges, and we have a carbon that doesn't have a full octet. So now we've broken the first rule of Lewis structures. This is going to be #3. Note that I like amides so much because #2 and #3 contrast an important point. You might look at it from a charge standpoint and say N+ should not be as good as C+, because carbon is less electronegative than nitrogen. Should be happy with that positive charge. But where you place the charges is not as important as the octet rule. Structure 2 gives everything a full octet. So even though it's N+ versus C+, #2 wins because it satisfies the first rule, fill all of your octets. Okay, our key structures in the upper left. Let's redraw this structure. There's really nothing, there are no lone pairs. So there's our structure. This is our original Lewis structure. That's not a proper Lewis structure, but our original representation. Now, let's think of a resonance form we can draw. This is one of the least common ways you'll see resonance get applied. It's with a carbocation. We are going to move this pi bond over, and we can do that because this carbon that has a positive charge doesn't have a full octet, so it can accept another bond. Normally, carbons already have a full octet, and they can't accept another bond without losing an old one. So when we do that, that's going to move the bond, and it's going to also move the formal charge. And so now we have the positive charge on the carbon on the left instead of on the right. So let's redraw our structure and see if we can come up with another resonance form. And this is kind of cheap, but we're just going to break that CC pi bond and draw whatever the outcome is. So we still have a positive on the right, we're going to get a positive on the left, and in the middle we're going to have a lone pair with a negative charge. So that's our last resonance form. So let's rank these. If you look, the top two structures are pretty similar. Both are carbocations. Neither has a full octet because they're carbocations. So which one's better? When we think about stability of carbocations, we think about their degree of substitution. The structure on the left is a secondary carbocation. The structure on the right is a tertiary carbocation. We would say the structure on the right would be the major contributor. Structure on the left might be close, but it would be second. This bottom right structure is just full of problems. We have two carbons that don't have full octets. We got a carbanion. I mean, this is a number 3, and you might even say there's no reason even for this to be discussed because it is such a minor contributor. And I would agree. But I said in the instructions, let's draw 3 resonance forms. So that at least fulfills our requirement for the problem. All right, problem number 8. This is our final problem. Let's draw this structure with lone pairs. That oxygen has 2 lone pairs, that oxygen has 2 lone pairs, and that nitrogen has 1. So that is our first resonance form. Let's redraw that structure and see if we can come up with another resonance form. So this fits the description for the most common instance for resonance, where we have a double bond next to an atom with a lone pair. So we could do that. And that would give us this structure. The oxygen on top now has 3 lone pairs and a negative charge. The oxygen on the left only has 1, has a positive charge, so there's a second resonance form. Let's do this again, reset, draw our original resonance form. And now we see our double bond has not only the oxygen with its lone pairs, but also the nitrogen with its lone pairs. So we can draw resonance from the nitrogen into the CO double bond, the carbonyl as well. Again, 3 lone pairs on oxygen. Now we have a carbon-nitrogen double bond. That nitrogen will have a positive charge, and this oxygen still has its 2 lone pairs. And that's our third resonance form. So let's compare these. One of these has full octets and no charges. That's the structure on the far left. This will be our major contributor. Now let's look at our structures on the right. Both of them have full octets. Where they differ is where they place the positive charge. In the bottom structure we have an N+. In the top structure we have an O+. Both have an O- as well. The bottom structure is considered to be a more important contributor because N+ is more favorable than O+ because N is less electronegative. Therefore, it is more willing to bear that positive charge. So here's how we get the rankings. This is the most important contributor, but we'd see some contribution from 2, maybe a little bit from 3. What we note for this is, based on these contributions, we'd expect for this oxygen to have quite a bit of negative electron density on it. Maybe more than this contributor alone shows us, because we see those contributions in the other minor resonance forms. I hope you found this video helpful. Please subscribe, like, or leave a comment or question. I'd particularly like to hear if there are any different types of problems that you would like to see in future videos. Thank you for watching, and remember, the links to printable copies of these problems and solutions are in the video description. Take care.